We're going to learn a couple new convergence tests, the ratio test and the root test. First, the ratio test. If we take a couple of terms of the series, the n plus 1 term and the nth term, and we take the ratio of those, and then we take the absolute value of that, and we look at the limit as n goes to infinity. If we get L and it's less than 1, then this series is absolutely convergent, and we know that absolute convergence implies convergence. So that's the first piece. If we take that ratio and that limit and absolute value and we get a number less than 1, we have absolute convergence. If we take that ratio and that limit and we get a number greater than 1 or that limit doesn't exist, then the series is divergent. And if we take that ratio and that limit and we get 1, then the ratio test is inconclusive. And so we've got three different things that may happen, and the test itself is taking the n plus 1 term, dividing it by the nth term, taking the absolute value, and then looking as n goes to infinity. Now, the proof of this ratio test is a little bit lengthy, and so there will be a link to the proof following this video, but the idea is this. For part A, we could prove it by showing that if the limit is less than 1, then the series is term by term less than a convergent geometric series, and so by the comparison test, then we would have convergence. If the second piece, which is where the limit was greater than 1, then the terms do not approach 0, show that the series diverged. And in part C, we can prove it by showing that we have two series, one that's convergent and one that's divergent, and they both equal a limit of 1. And in fact, we can see that one right now. So here are our two series. We know this is a convergent P series. We know this is the harmonic series, and it diverges. So if we applied the ratio test, first of all, to 1 over n squared, we would take the n plus 1 term divided by the nth term. And so here it is, and we don't need the absolute values because it's all positive anyway. So here's the n plus 1 term divided by the nth term. Flip it over and multiply. It looks like this. Multiply numerator and denominator by n squared. And we have 1. Here we have 1 plus 1 over n. And then we know that as we let n go to infinity, this one's going to go to 0, and so we get a limit of 1. Now if we apply the ratio test to our harmonic series, we take that ratio, we have 1 over n plus 1. We know harmonic series are always positive as well, so we don't need the absolute values. Or 1 over n, flip it over, multiply numerator and denominator by n, we get this, and then as we let n go to infinity, that goes to 0 and we get 1. So obviously when we do the ratio test and we get 1, you know nothing. It's inconclusive. We'd have to apply some other test. Now we also have the root test, and very similar type of results, and so it's easy to kind of group the two R tests, the ratio and the root test, together to help us kind of remember that. So the root test is this. If we are looking at a series and we take the absolute value of the term, so looking at the absolute, and we take the nth root of that and we let n go to infinity. If the limit here is a number less than 1, then this series is absolutely convergent and therefore convergent. However, if when we do that the limit is greater than 1 or the limit doesn't exist, then the series is divergent. And if that limit equals 1, then the root test is inconclusive. The proof of this is actually very similar to the proof of the ratio test, and there is a link to that proof following this video. One last thing on these ratio and root tests, like I said, they're grouped together because you saw that as we take these limits, same kinds of things. If that L is less than 1, we've got absolute convergence. If it's greater than 1 or doesn't exist, we have divergence. If it equals 1, we don't know anything. Time-saving hint, if you apply the ratio test and you get L equal 1, don't bother trying the root test. We have to try something else, but not the root test, because you're going to get 1 again, so don't waste your time. And if L equal 1 in the root test, don't try the ratio test. Same thing. Both tests are going to fail And so if you find that one of them fails by giving us L equal 1, don't bother with the other one.